Okay, today we're going to finish up section 6.2. This is example 4 in the book. An experimental population of fruit flies increases according to the law of exponential growth. That's what we learned about yesterday, exponential growth model. It said if y was a differentiable function such that y is greater than 0 and y prime equals ky, that was the rate of change of a variable y is proportional to the value of y. Then we know that y equals ce to the kx. So it's the formula we were dealing with yesterday. So because they said according to the law of exponential growth, we know y equals ce to the kx. So now keep reading. There are 100 flies after the second day of the experiment and 300 flies after the fourth day. So let me look about that. Not kx, but kt. I tell you what, I need to read my glasses. There were 100 flies, that's the amount of flies. After the second day, that's time equals 2. So there's that fact. And then there's another fact. And there were 300 flies after the fourth day. So there's another fact that we'll be dealing with. Approximately how many flies were in the original population? An original population would happen at time equals 0. So we're going to take the first fact and plug it in. So the very first thing we're going to do is deal with those two. So yesterday the t was 0 and we were able to figure out what c is, but this function is going to work a little differently, this example. So now let's take this second fact and see what we get. So we get 300 equals ce to the k times 4. Plug it into the same equation, so we get 300 equals ce to the 4k. So I have two variables and two unknowns here. I have a system of equations right here. So I'm going to solve them using substitution or elimination. I think I will solve this first one for c. And I'm going to take it and I'm going to plug it in right there. Okay, so I'm just substituting it in. I'm going to go ahead and put that all the way over like this. And so I'll get 300 equals 100. Let's look what we do right here. We're dividing like bases, so we need to subtract their exponents. So 4k minus 2k is 2k. Let's get k by itself, so let's divide by 100. Now k's trapped as an exponent, so log base e of 3. Oh, that's looking a little bit messy there. Equals 2k. So divide that by 2 and we'll get k. So k is log of 3 over 2. So now let's go back and let's plug it right there for k. All right, and we'll plug in for k this ln of 3 over 2. And that equals c. And then you just pick up your calculator and see what you get. All right, I got 33. Let's look at this. Let me try to rewrite this over here somewhere. Where can I rewrite it? me just blank this out a little bit. No, that didn't work. We'll just look at it right here where it is. Let's divide the 2. And then I've got e to the ln base e of 3. Those cancel each other and it's just 3. And 100 divided by 3 is 33. So we didn't really need to pick up our calculator had we been thinking about our logarithm properties. Okay, we're not done though. We know what c is. So now we can go back to our original equation. That's the downfall of the whiteboards. It's just not enough room. So let's go back to y equals ce to the kt. We know what c is now. It's 33. And we know what k is. Let's see. It's ln of 3 over 2. Let's get that as a real value. Ln of 3 divided by, ln of 3 divided by 2. 0.549. So 0.549t. And now we can figure out the last thing they wanted to know, which was how many fruit flies were in the original population right here. So we don't know y, but plug the t in, and you get a 0 up there, and e to the 0 is 1, so you get y equals 33. And you might remember, so there were 33 flies in the original population. You might remember back to this model that we wrote down. Once you find c is the initial value of y. So I really didn't have to do that last step. Once I found c, that was the answer.